and a longer string, and then you whirl it around your head, what happens is, and here's the ladybug that you put in the can, right? And as you whirl, I know, poor thing, as you whirl, once you stop doing this, you'll have a very, very dizzy ladybug, kind of like staggering around, right, when you let her go. So here's the ladybug, and what happens is that as the can is being rotated around your head, she experiences a force towards the center. That force is the centripetal force. Where does that force come from? It comes from the bottom of the can, pushing up on her, because her inertia is trying to push her in this direction, right? She's trying to go off. So if the string were to break, what happens is the can just travels off in a straight line. That's inertia. I'm sorry?
Where's the ladybug? In the can?
The ladybug is in the can. She goes with the can, right? Okay, so that would be the effect of centrifugal force. Centripetal force is the string, the tension on the string that's pulling towards the center, right? Okay, introducing the concept of angular momentum. We have spoken of momentum in the past, like we had talked of momentum as like a measure of the difficulty in stopping something from moving. Angular momentum is like a measure of the difficulty of stopping the object from rotating. So that is a product of the body's rotational inertia and rotational velocity about the axis. And we'll see applications of this and it'll make more sense. Just like we had conservation of momentum in the past, which was conservation of linear momentum, now we have conservation of angular momentum, which basically says that if you don't put in any extra force or any extra torque into the system, an object that's rotating with a certain momentum, rotational momentum, will just keep rotating with that same rotational momentum. So the angular momentum will not change. It will not increase or decrease unless you apply an external torque, which is a force multiplied by a lever arm. Right? That's what conservation of angular momentum states. So, illustration of this. Here is like a stone tied to a string that you're whirling around your neck with a certain radius, certain velocity, certain mass. We had said that linear momentum was mass multiplied by velocity. We saw this in a previous lecture. Now if you take that linear momentum, mass multiplied by velocity, and multiply it by the radius, you end up with a new term called the angular momentum. So the angular momentum is merely the linear momentum that we've already seen, multiply that by the radius of the path that is traveling upon. That is also equal to a new entity that we're introducing, I, which is called the moment of inertia, multiplied by omega, which we've already seen. Omega is a rotational speed. So just like in linear momentum we had mass multiplied by velocity, here we have moment of inertia multiplied by angular velocity. So I, the moment of inertia, is the angular rotational equivalent of mass. So this is not a correct usage, but one way to help us to understand this is to think of this as linear mass, ordinary mass, linear mass, and I is rotational mass. So here is, you've all seen a ballerina, right? Or an ice skater, right? An ice skater or a ballerina doing a pirouette. And what happens when the ballerina pulls her arms in? She travels faster, right? And when she puts her arms out, what happens? Slows down. What is happening is conservation of angular momentum. So here is the ballerina, right? And what happens is when her arms are out, she has a large moment of inertia. Remember that we said that your rotational inertia is greater if your arms are out. It's harder to turn. So big I, big inertia, multiplied by, in this case, a small omega, a small rotational speed. So rotating slowly. Pull the arms in, and what happens is I becomes smaller. If I becomes smaller, then W has to become bigger. Omega has to become bigger. So that these two terms are equal because of conservation of angular momentum. So this is why when you pull your arms in, your rotational inertia decreases, which means that your rotational speed has to go up, and that's why you spin faster. Cool? And just a reminder for you to go ahead and look through the questions that are after the lecture slides, and just go over them, make sure you understand the concepts, and if you have a difficulty with any of them, come and check with other students in the class. If none of the other students understand the concept, then come to me to talk about it, right? And that's part of your responsibility.